Hi everyone, in this lecture we are going to continue the next topics in module 7, and in the first lecture I have discussed that we are going to learn how to calculate the internal forces at a specific location of the beam and along the beam. Okay, and we already discussed how to calculate internal forces at a specific locations, and in this lecture we are going to learn how to calculate the internal forces along the beam, and for this purpose we are going to develop the internal forces diagrams. Okay, and to develop the internal forces diagrams, whether it's axial, shear and moment, we will discuss two methods in this module. The first one is using the equations, and the second one is using the relations. Okay, this lecture and the next lecture is going to focus on how to develop these internal force diagrams using the equations. Okay, so these internal forces diagrams, okay, tells us, okay, the internal forces along a beam under action of the loads, okay, action of the forces or moments. Okay, they provide useful information, okay, related to the maximum internal forces, but it could be the minimum. Okay, remember we have the sign conventions, whether it's positive or negative, right? And then where is it located? Where is that maximum or minimum internal forces are located? And the main purpose of doing this is to calculate is to use it in terms of the design of the beam, to figure out what is the dimension of the beam, okay, and what maximum load that we can apply to the beam. Okay, but however, don't worry about that things yet. You guys will learn it in more advanced class when you take the mechanics of materials or deformable bodies class. Okay, but in statics we will just learn how to construct these diagrams and figure out what is the maximum internal forces and where they are located. Okay, and then let's continue with one example problem, which is the same example that we discussed when we learn how to calculate internal forces at a specific location. Okay, so it's a simply supported beam. Okay, so it's a pin supported at A and then roller supported at B. Point force is applied at midspan of the beam, vertically going downward, and another point force is applied at point B, going to the right, and it has magnitude of P/4, okay, for the point force at B, and it has a magnitude of P for the point force located at the midspan. Okay, and in here we take that the X, okay, is going from left to the right, from A to B, and this X, why we need to define this X? Because remember, in here we are going to develop the equations or the functions, and that functions is in terms of X. Okay, such that in here what we are going to find is the internal forces equations. In here, N is the axial forces equations, Vx is the shear equations, and Mx is the moment equations. Okay, that describes the internal forces, moment, shear and axial along the beam under the action of these forces. Okay, when I solve this problem, the first thing that I like to do is to define the ranges in these problems. Okay, and these ranges is determined based on the discontinuity that is introduced by either the point load or point force or moments, or distributed force that's applied to the beam, or by the reaction support that exists in the beam. Okay, that exists in the beam. Okay, so in this case, when I figure out when I try to find the range in the, for this example problem that we have in here, there will be two ranges. Okay, so the first range is this guy over here. The second range is this guy is over here. Okay, alright, so range 1 is defined from x equal to 0 to L over 2, and range 2 is defined from x L over 2 to L. Okay, so how could I define these two ranges then? If we start from point A, right? Okay, and remember at A we have AY, AX, right? At B we have a BY, right? So when we figure out how many ranges there are in the problems, so we start from point A, then we go to the right, corresponding to the positive x direction over here. From 0, right? From x equal to 0 to L over 2, right? There's nothing else applied on the beam, right? So everything stay constant or stay the same, okay? And then the discontinuity is introduced at x equal to L over 2 when we have a point load applied at that location, okay? And that's the reasons why in this case range 1 stop at x equal to L over 2, okay? And afterwards we start the range 2, which is starting from x equal to L over 2, right? And then when we go to the right again, everything stay the same until the end of the beam where x is equal to L. Okay, so that's how you figure out the ranges in the beam. Depends on the problem that we solve, right? And the range are determined based on the discontinuity that are introduced by the applied loads or by the reactional support. Okay, and after figure out the range in here, okay, then we will make a cut. Okay, we will make a cut somewhere in the range 1 and then somewhere in the range 2. Okay, so we will make a cut 1 and cut 2. Where is this cut 1 and cut 2 located? We don't know exactly, but it should be somewhere within the range that we already defined in here. Okay, so let's start for range 1 first in here, such that everything will become clearer. Okay, so we start from range 1 where x is defined from 0 to L over 2. Okay, and in this case let's define that the distance where we make the cut as x. Okay, as x. Okay, because we don't know where is it located, but we know it has to be somewhere between 0 and L over 2 within the range 1, right? So we just define it as a x because we already use x to define the horizontal coordinates of the beam, right? So let's use x, which is the location where we make the cut 1. Okay, so when we make the cut 1, we can divide it into left hand free body diagrams and the right hand free body diagrams, and it's good to sketch it right now. That here I have my left hand free body diagram, here I have my right hand free body diagram, and remember in here we're looking at a range 1. Okay, and we cut at a distance x, right? And we know the total length of the beam is L, so the rest of the length of this right hand free body diagram is L minus x. Okay, and then we have over here is AY, over here is AX, right? And then we have in here is P, right? And then in here we have BY, and then in here we have P over 4. Okay, and remember that the distance right here is we know that this is L over 2, right? Okay, so this distance right here is L over 2 minus x. Okay, and it's almost complete, the free body diagram that we draw in here, except that we have to include and then let's say this point as cut 1, right? Label it as 1 right there. So this is m of x. We have to draw the internal forces. When we make the cut, we see the internal forces, but in here notice that I use m as a function of x. Okay, so this m of x is a m as a function of x, not m multiplied to x. Okay, so please differentiate this m x in here is m as a function of x. Okay, and then we have v, the shear, as a function of x, and then the axial force N as a function of x. Okay, notice that all of the directions that I draw in here are in positive sign convention. Okay, same thing in the right hand free body diagrams. We have m of x, we have v of x, and we have n of x. Okay, and all of the direction that I draw in here are in positive sign convention as well for the right hand free body diagrams. And all of these internal forces, you guys have to remember that it's occurred at this point right here. Okay, the sketch may be drawn a little bit far away from that point for a clarity reason. Okay, so right now we have two options, and whether you would like to calculate the mx and xvx on this first range, okay, using the left hand free body diagrams or the right hand free body diagrams, it should give you the same result. Okay, and it turns out if you choose the left hand free body diagrams, it will be much easier, but for this lecture I'm going to show you how to obtain those functions m, v, and n using both diagrams. It should lead to the same expression. Okay, it should lead to exactly the same expression. Okay, so taking sum of the moment at 1, which is at this point right there, I have minus ay times x, right? Then I have my plus m of x equal to 0, so my m of x is equal to ay times x, and we have calculated ay before. Ay is p over 2 from previous example, and ax in here is negative p over 4, right? So we have p over 2 times x. Okay, and notice that in here the moment is a function of x, and it's a first order equations, right? First order expression. It's a first order polynomial, right? So it's a linear line. Okay, so afterwards we can continue by calculating the v of x, and then we can take the sum of the forces in the y directions. We have ay minus v of x equal to 0, so my v of x is equal to ay is equal to p over 2. So along in this first range, vx going to be a constant with a magnitude of p over 2. Okay, and then when I do sum of forces in the x, right, I have n of x in here and ax over here, right? So n of x plus ax equal to 0, so I have my n of x is negative ax, and negative ax is negative p over 4. So in here we have p over 4, and this indicates that n of x in the first range is also a constant function, okay, with a magnitude of p over 4. So we can continue with this right hand free body diagrams in the first range, and I will show you that you should obtain exactly the same expression. Okay, so no matter which diagram that you choose, left or right, you should obtain the same expression. Okay, as long as you start from the same reference point for the x. Okay, so let's do in here sum of the moment at I in the right hand free body diagrams. Okay, I have by times L minus x, right? Then I have minus p times L over 2 minus x. Then I have minus m of x, okay? Then this is multiply, right? So my m of x is by L minus x plus minus p times L over 2 minus x. So my by is p over 2 from what we have calculated in previous example. So here we have p over 2 multiply with L minus x, and in here we have p multiply with L2 minus x. So we expand the expressions. We have p over 2L minus p over 2x. Here we have minus p L over 2. In here we have minus plus px. Okay, this will cancel out, right? And then when we take this subtraction over here, we will obtain that m of x is equals to p over 2 times x, which is the same expression that we obtained from the left hand free body diagram. Okay, and then we can continue with the sum of the forces in the y. Okay, we have v of x, right? And then in here we have negative p plus by equal to 0. So my v of x is p minus by. Then I have in here is p over 2. So again, this expressions is the same as what we obtained at the left from the left hand free body diagrams. Lastly, we take sum of the forces in the x. We have negative n of x plus p over 4 equal to 0. So my n of x is equal to p over 4. The same expression that we obtained from the left hand free body diagram. Okay, and we finish with the range 1. Okay, right? And then right now we are going to continue with the second range, where x is defined from L over 2 to L, right? And to calculate the equations in the second range in here, we have to make a cut somewhere in the second range. Okay, and let's call that the distance of that cut as x, because we have defined that in here x is defined 0 at a, and then it goes it is increased when it goes to the right. So we cut, let's just use x as the distance where we make the cut at the second range. Okay, so we make a cut right here. We will divide the structures, the beam in here, into the left hand and the right hand free body diagrams. Okay, so I'm going to sketch. For second range, we have x defined from L over 2 to L. Okay, and this is the left hand free body diagram. This is the right hand free body diagrams. Don't forget we have the force P right now on the left hand free body diagrams. We have AY, AX, which is minus P over 4, P over 2. And then we have BY, which is P over 2, and we have this P over 4 right here. Okay, and then the distance, this is L over 2, this is X, such that the distance in here is X minus L over 2, and the distance right here is L minus X, because we know the total length of the beam is L, and we make a cut in here. Cut number 2 is located at a distance X from point A. Okay, so divide this line. So this is our left hand free body diagram, and then this is our right hand free body diagrams. And it turns out the right hand free body diagrams is easier choice if you can write it here, but I will show you how to perform the calculations using both diagrams. Don't forget, this is m of x, v of x, and n of x. this is m of x, v of x, and n of x. Okay, so when I do the sum of the forces, let me do the sum of the moment first. At 2 in here, right, I have m of x, right, and then minus ay times x, okay, and then plus p times x minus l over 2, okay, and set this equal to 0. When you simplify these expressions, I think you will obtain this. Alright, and then doing sum of the forces in the y, you will have ay minus p minus vx, okay, set it equal to 0, you will obtain vx is ay minus p, ay is p over 2, so minus p over 2, okay. And then when you do sum of the forces in the x, here you have nx and ax, okay, so nx plus ax equal to 0, so your nx is negative of ax is negative p over 4, so in here is equal to p over 4, okay, so because it's negative of negative p over 4 is positive p over 4. Right, and then when you solve it using the right hand free body diagram, you should obtain exactly the same expressions. When I take the sum of moment at 2, right here I have negative m of x plus by times l minus x, okay, l minus x, and equal to 0. I have this m of x is by is p over 2 times l minus x, so here is p over 2 l minus p over 2x, which is the same expression that we obtain right here, right? Okay, then sum of forces in the y, we have by plus v of x equal to 0, then my v of x is negative by negative p over 2, so again the same. And lastly, sum of forces in the x, we have negative n of x plus p over 4, right, negative n of x plus p over 4, so my n of x in here is p over 4. Okay, so now we finish in writing all of the equations. Then we will use these equations to plot the internal force diagram. Okay, so to summarize, let's summarize what we have obtained. That m of x that we obtain in here, right, is equals to p over 2 times x, and then pl over 2 minus p over 2 times x, and this is when x is from 0 to l over 2, and this is x from l over 2 to l, okay, and then v of x is defined as p over 2 negative p over 2, that this is from x is equal to 0 to l over 2, and this is x from l over 2 to l, okay, and then n of x is p over 4, right, p over 4 from x or you can write it as p over 4 x from 0 to l, okay, because there are constants along the length of the beam. Okay, once we have summarized this, we can make another sketch right here. Okay, so I'm going to resketch the beam. We have P, then here we have P over 2, here we have P over 2, right, then we have here is P over 4, and here is P over 4, which is AX, right? Negative is going to the left, okay? And I can draw the free body diagrams, okay? So this is the x-axis, right? And then this is my y-axis. This is m of x, right? This is the x, right? So at x equal to 0, right? M is P over 2 times 0, so it's 0. So this is it. At x equal to L over 2, right? This is P over 2 times L over 2, so it's PL over 4. And it's positive, right? And it's a first order polynomial, so it's a linear line, it's a straight line, okay? And then when m is equal to, at x equal to L, right? In here we have PL over 2 minus PL over 2, which is 0. So we have a positive moment in here, with its maximum moment is positive, is PL over 4. Okay, and then we can continue again by sketching the this is x, and then right now v of x. Okay, in the first range from x 0 to L over 2 is P over 2 positive, so it's P over 2 positive, and then on the second range is negative P over 2 negative. Okay, so this is the diagram looks like. Okay, and then the last one is for the axial force. We have x here, this is n of x, right? And it's P over 4 along the beam. It's positive P over 4. Okay, so if I further ask you the questions, what is the maximum moments, then this is the answer, right? PL over 4. What is the maximum shear? It's P over 2, right? And then what is the maximum axial force? Is P over 4. Okay, where is the axial moment located? It's located at the midspan where P is applied, right? In the middle, right? Okay, and with that, and one more thing that I would like to show, that if we add right here, right, this is P over 2, right, and then this is negative P over 2, but the overall magnitude in here is P. Okay, and notice that in here the point load is P. Coincidence? I think not. Okay, and we will discuss this later when we talk about how to construct these diagrams using relations. Okay, but for the meantime, if you're using the equations, this is how you construct the diagrams. Okay, so first we have to identify the ranges on the beams. It can be different, depends on the problems that we have to solve. Okay, after define the ranges, make the free body cut on each ranges, right, on each range, and then based on that cut, form the internal forces equations, the m of x, v of x, and n of x. After you obtain the equations, plot the diagrams based on that equations. Okay, so one more thing I would like to say, these equations tells you, right, the internal forces along the beam. Okay, so the internal forces at midspan is calculated in here. It's PL over 4 for the moment. Okay, and then at 0 is 0, at L is 0. And then how about at L over 3? At L over 3 is going to be P over 2 times L over 3, right? Using these equations right here, you will obtain PL over 6. Okay, and this result is the same as what we obtained from the previous example, right? When we discuss moment or internal forces at a specific location. Same thing in here. If you calculate V at L over 3, you will obtain P over 2, right? Because it's right here, right? And then same thing in here. Same thing in here. It's the N of x and V of x for at x equal to L over 3, which is P over 4 and P over 2. Okay. With that, I think it's enough for this lecture. And as usual, please let me know if you have any questions.